Hey, this is OXDF, and today I'm looking at Known, the second challenge from Flare-On 2021. This was a binary that I actually, when I solved it at the beginning of the challenge, I believe I wrote out a really solid notes, if not a complete blog post then when solving it, but two different people reached out to me on Twitter and asked me to show it in a video, so I'm going to go ahead and give it a shot here. I've gone ahead and created a folder called Known that just has the downloadable in it here, so I can go ahead and extract that. I give it the password Flare, and see what I have. There's a single file called UnlockYourFiles.exe. It's a 32-bit executable for Windows. And then there's also a directory files. So we'll take a look at that. And it's just a handful of, let's see, 6 files here that all have a .encrypted extension. And so there's a PNG, a text, a GIF, critical data.txt, Latin alphabet.txt. I actually didn't notice Latin alphabet.txt when I first originally solved this. That's kind of an interesting one. But it's kind of a cool example. It's 26 bytes long. So I can already start to make some assumptions about this. If these are encrypted files, then the encryptor is almost certainly doing it byte for byte, like a stream cipher and not a block cipher, because 26 bytes would be a pretty weird block size. And so it kept the same size as the input. So that'll be useful to know going forward. Let's see. Other than that, it's probably good to go ahead to, let's jump over to a Windows VM here. And I've got my Flare on VM. I've created a different folder, but with the same thing. I've already extracted the stuff here. If I go ahead and run UnlockYourFiles.exe, there's a warning thing. So this is supposed to be ransomware has already been run. This is the exe that's going to unlock it for me. If I pay them, they'll give me the key, and then I can put the key in down here. There is this base64 encoded string that I'm supposed to use as a key. Anytime I see base64, it's worth trying to decode it. So I'll come back here to Linux and just echo that into a base64 decode and see it's dangerous to add plus rar alone, rotate right alone. Take this. Okay, so I'm gonna want to watch out. I'm reading that as the encryption here is not good, and I can break it. If I can reverse it and figure out the algorithm, I can probably figure out how to get my files back. So if I do enter a key, please subscribe and enter. It says it runs through the files that were in the encrypted directory, or in the files directory, and it says it's decrypting them, decrypted 6 files. If I open it up here, let's see, I got kappa.png. It can't open it because it appears to be corrupted or is too large. The text file looks like complete junk. So what's happening here basically is I gave it a key. It tried to decrypt with that key. It's not the right key, clearly. So the results are just garbage. I'm gonna go ahead and delete those clear text ones because I want to try again later. I want to get the key. One thing that is interesting to try is, so can I give it some known encrypted text and see what it does with it? So I'll do something like a Python 3 -c print a times 64. Does that work? Yep, okay. I don't know why, but I like capital A better, so I'm going to do that. And then I will direct that to files test.text.encrypted. And then let's see what happens if I run that again. Does it pick up on it? Please subscribe. And okay, so 7 files. It did try to decrypt it. I can come over here and take a look at it. What does it produce? Still clearly garbage. I wonder if what's my hex editor on this VM? I don't even know what I have. I'm not sure if I have a hex editor. I will see what's the easiest way to do this. I'm going to pause the video real quick and copy this file over to my Linux VM. Hold on one second. Okay, I'm back and I've got the file over here. I can do easily an xxd test.txt into less. And so what's neat here is, I'm going to make this a little bigger. So I can see that there's definitely a pattern here. Regardless of the fact that my please subscribe key was longer than 8 bytes, it looks like 1, 2, 3, 4, 5, 6, 7, 8, and then it repeats. And so it looks like it's somehow using the first 8 bytes of, or it's somehow using the password to generate an 8-byte key, and then those bytes are applied here. Again, because my input was all A's, every 8th byte is the same. So, and except, on the end here, there's this 7 dCB, There's 64 here. That's probably the /r/n, the new line in Windows, is 2 bytes. So that's probably why that's different. Okay. So we got all of that. Not much else here. Let's go ahead and open this up in Ghidra. Ghidra is my tool for reversing of choice. When you download Ghidra, you download it into, it's a zip file, and you can unpack it and run it. What I usually do, just as an FYI, if I do user local bin Ghidra, I just create a symlink. So this Ghidra run script is how you start Ghidra. I always just create a symlink and user local bin, so I can just type Ghidra, and that's how it opens up really cleanly. I'm going to need a new project. It's a non-shared project. Let's put it in the known directory. Project name will be known. And then we need to import the binary into it. So there is UnlockYourFiles.exe. It recognizes it as the 32-bit executable. And we don't need this stuff. We're going to drag it up here into the code browser because that's where we want to be. And it's going to say it's not been analyzed, but I want to analyze it, yes. And I'll just accept the defaults. I'm going to, one of the pieces of feedback I've gotten is that people have a hard time seeing some of the Ghidra stuff. So let's see if it's under listing display, font 20. That looks bigger. And where's the other one? It's under decompiler, display. I don't know why these look so different for the same thing, but make that 20 as well. Awesome. Okay, so first place I always look when I'm importing a function like this, or a binary like this, is to come at the functions. A lot of times I'm going to see 100 functions there, 1,000 functions there, and so that's overwhelming. You're not going to just look at them one by one. But here I actually only have a few, not that many. I'm still going to start an entry because that seems like a good place to start. And you're always going to have an entry because that's, the binary has to tell the OS, here's where to start. When you're dealing with Windows EXEs especially, a lot of it really just comes down to, can you rename your variables, your functions? Can you retype your variables and your functions to make them make sense? Because what I want to do is have this over here basically tell me exactly what it's doing. So a lot of that really comes down to going ahead and using the Windows API documentation to understand what the functions are doing. So here I have the function getStdHandle. So let's go ahead and just Google that and see, look for that docs.microsoft.com link if you can get it. That's the most useful way. Okay, so the syntax here is it's going to return a handle called WinAPI, and it takes in a D word, that's an integer. And then down here it tells us exactly the standard ones to expect, -10, -11, -12. These FFF things look like they don't match that, but if you come over here, this call right here to the get standard handle, right before it's pushing -a, let's see if I can change that, convert to decimal. So that's -10. So great, it's pushing -10. We know from here, -10 is standard input. And so we can rename this variable standard_in _ h for handle. In fact, I recognized the type up here is a handle, so that's good. And then this one, -5, is this -b right here. Again, I can convert it to a signed decimal, -11. -11 is standard out. And so this time this is a local variable versus this is a global variable, but I can rename it just the same. Standard out oops, not D. Let's fix that. Rename. Cool. So then it's coming in here and calling set console text attribute. Now, having seen this run, I feel pretty confident this is what's causing that red background. We can come up here, set console text attribute. Sure, there's a typo in there. Let's see if it fixes it. Yep, and there's my docs.microsoft link. This thing takes a handle to a console output object. So it's passing in the standard out handle, and then it takes attributes. And if I come down here, attributes there's a link to the character attributes. And there's all these constants that, underground, background red, foreground red, etc. And in this case, you saw in the last one, they actually define the values right underneath them, and this time they don't. Microsoft is really inconsistent about that. You can do some Googling here. We can Google see what the best char info structure. Maybe this will give us some information about what it is. Oh yeah, here we go. So we have CE. Let's see if I didn't think that was going to work. So we'll see. Now, a lot of times when you have things like this, these are like flags. And so what it's doing here is if the 1-bit is set, it's foreground blue. If the 2-bit is set, it's foreground green. If the 4-bit is set, it's foreground red. And so you could technically have all 3 of those ORed together. So when we have CE, we have, let's see, C, so E is pretty easy. It's 1, 2, 3, 0, like that. C is 2 less than that, so it's going to be 1, 1, 0, 0, like that. So that's what we're passing in. So it's going to be foreground green and foreground red. Not sure, because there's the 2-byte right there is on, and the 4-byte. And then it's going to be foreground intensity will be a part of it. Not foreground blue, not foreground green, or background blue, background green. It's going to be background red. That's this last one. And then it'll be background intensity is going to be intensified as well. So that's what this CE translates out to. And if that's not clear to you, you can look at, go find a binary calculator, put in CE, and then look at these different bytes and how they impact it. You can convert all those to binary and you can see how they line up. So, anyway, it's not super important, but we can see it's setting the colors as we saw. And then it's writing to standard out to the standard out handle. The intention message, the message is 70A long. Again, I've done this before, but we could always come over here and Google write console A and figure out. In fact, we'll do it right now. And we're just looking at, what are the things it takes, and are our variables, can we figure out what our variables are? In this case, we probably already know, but so let's see, try to see if I can view both these at the same time. Okay, so it passes the handle, cool. The buffer that's going to print, that's this, we can look at that in a second. The number of chars to write, that's 0x70A. The number of chars written, which is this, it's passing in a null buffer, so we're not gonna get that back. And then a reserved thing that doesn't matter. A lot of these functions use this word where it allows you say, I want to write up to this many bytes, and then it will it'll return to you in this value. So you pass it an address, and it will fill that address in with how many bytes were written. And so in this case, it just doesn't care. And then it's going to read from the console using the standard in handle into, well, let's actually look this one up as well. Read console A. And function is going to take, so console input handle to the input, so standard in, the buffer that it's writing to, so 14. And now we remember, and let's look at this message real quick, because that'll help us. This global here, attention here. So we can see that it is, we were getting 70A, and you can see that it's all condensed here down to 70C. So that makes sense. Looks like this whole buffer is in account. How do I view this whole thing as a string? I'm not sure how to expand this. We could do a search for strings to see the strings and find this. Search. We know that it's got a bunch of that at the beginning. I think we do. Huh, maybe that's actually not in the strings and it gets set. No, that's bizarre. I wonder why that's not showing up. Well, I'm not going to stress about it right now. I can always come back to my Windows VM and see specifically that's the attention, blah, blah, blah. Here's this is the blob, and then all the way up through here is probably what's put out. And then it's asking for the key. So I know I have a pretty good feeling that this buffer right here is going to be the key. User key. It's looking to read up to 8 bytes. So when I put please subscribe in there, it was like please was all that got read, and the rest, is just sitting in the standard in buffer. This is going to be the bytes, number of bytes read. Bytes read as key. And that's the end of that. Now it's going to pass the key into this function right here, and then it's going to exit. And so we have kind of, I don't know what to call this. We'll call this decrypt with key. We don't know what it does, but just having seen what the program runs, that's basically where it can happen. So we're going to feel pretty good that's what's happening there. So I think with that, let's go ahead and dive into this function. So we have set current directory A. And again, you can start to guess, what is this thing doing? And it's almost certainly setting the current directory, but it's always useful, especially when you're beginning, just to look at this and say, okay, so it's taking a path name and it's returning a Boolean as to whether it succeeded or not. And there's all this detail most of the time about the different parameters and what they mean, and what does it mean if it's null, and so you might ask, like, what does it mean if it's is it a relative path or an absolute path? So let's see what it says. The path in a directory, it may be a relative path or a full path. In either case, a full path of the supplied directory is calculated and stored as the current directory. So cool. That the return value is either going to be non-zero for success or 0 for fail. Cool. And so we can look at this global here by double-clicking on it. I'm trying to make it readable, so I kind of move this back and forth a lot, and it's just the word files. So basically that's a relative path. It's going to take your current directory, look for a files directory. If that fails, it's going to pass, let's see what this says, something about set current directory, blah, blah, blah. It's going to call this. Let's see what that function does. It's doing a lot of writing console, and then it's exiting the process. It's getting last error. So I don't need to even dive too deeply into this. Enough to say I could go back to the Windows VM, try to run this in a directory that doesn't have a files directory, and see it fail. But I'm going to say this is pretty clearly print error and exit. And look, it's neat because when you rename it, you see it renamed here, here, and here. So this, it's taking in this error string or string template, and it's using that to make the error message and exit. Let's see, let's rename this set current res. Okay. Does it use that again? Oh, it does. So this is more of just like a generic res. One thing you'll see a lot is that when you have functions that return and then get checked, a lot of times they don't, they reuse the same variable space over and over again. So you just kind of got to get used to seeing that. Okay, so now find first file A. Again, we want to have our reference up here. See what this function does. So searches a directory for a file or subdirectory with a name that matches a specific name or a partial name if wildcards are used. It takes in a file name, and then it also takes a buffer, which is going to return an LP find file data. So the first thing it's describing is star.encrypted. So it's looking for all the files that are that end in star.encrypted. That makes a lot of sense with what we saw earlier. And then it's going to return, this is going to be our file data. File data. All right, and then what's the return address look like, or the return value is a search handle used for subsequent calls. So this will be like our find file handle. Okay. If that returns -1, it's going to print error and exit. Otherwise, it's going to enter this while loop. In this while loop, we are going to start with a function here that takes the file name and this variable, does something else with the file name. Then I can see this same buffer that was passed to the first function is passed to this next function along with the file name and param1. We remember what this was called with. If not, we can go back to entry and see that when we called decrypt with key, it was passed the key. So when we come in here, we can really at the top rename this variable user key. Cool. So now we have the function down here that takes in the some couple stuff and the key. And then it is incrementing this local 8, which is some sort of count variable. One thing I'll remember, this is where it's useful to look at the details that I kind of skipped through, but if I jump over here, one thing, at the end it prints out number of files decoded 7. So it's the fact that it's keeping a count as it runs through here, that's interesting. This could be the count of the number of files that were written, and this message down here could be where it prints that out. Let's look at that real quick. Yeah, so it's taking in, let's see, rename this variable to count. It does something with that, and then it writes to the console number of files decoded. And does local 14 or count pushed in? Somewhere down here, it must, one of those things must, yeah, so here local 14 is written. So somehow this must maybe takes it from a int to a string or something, but somehow the result ends up in local 14, which is then passed into this write console. So I think we can put, we can rename this pretty quickly. Write num decrypt message. Now, I'm going very quickly through this function because I don't think it's probably important to what I need to solve the challenge. If I should be aware of the fact that I was quick through this one though, so that if I go through all this and I don't see what I'm looking for, that I'm, and I go back to the part of, okay, where did I make assumptions? Where could I be wrong? That I know I could come back here. But I think, pretty clearly, here's the find first file, here's the find next file call. So in this loop, basically, let's look at this loop. So it starts off with a find first file, then it enters a while true. It does some stuff, increments its count, and then it does find next file on the find file handle and the data again. So it's going to write a new data information about the file, and it's going to use this handle to find the next file. If that res is 0, so what happens from find file A here? Where's our return value? If the function succeeds, the return value is the search handle, blah, blah. If it fails or fails to look at files that match the pattern, it returns invalid handle value. Okay, one thing we can check, I wonder if, so this is a cool opportunity. I don't know if this is going to work or not, but we can do set equate and see if invalid file handle here is in here. It might not be. Okay, so this is kind of hit or miss. It's really useful, and I'm sure it'll show up useful later on in this one, but it didn't work here. So I'll go into what that was doing later. But I can make a guess that invalid file handle. We can try Googling it again, see if we find it. But even if not, I'm guessing that's probably 0. Not sure why that's hanging. Ooh, it's redirecting. Let's see. I have no idea what I stumbled into here. This is probably, oh, let's see, public const invalid file handle. Can I make you bigger? Wait, did my VM crash? Oh, equal to -1. Okay, so that's not, oh, if it's not equal to 0. So I'm guessing it returns 0 on success. Maybe I misread that. 0 is successful, so it found the right thing, so it's going to continue looping. Whenever it returns something non-zero, that means that find file A was not successful, and it's going to break, and then it's going to do a get last error. If dvar1 is equal to 0x12, then break. Otherwise, it prints an error and exits. So we should really look at what is get last error doing. Again, I'm just happy to find the docs.microsoft.com links. Let's see what comes up here. Okay, it simply retrieves the calling thread's last error code value. The return value is the error code. The complete list of error codes, let's see this link here. That's probably what we're looking for. I don't know why my internet got so slow here. Let's see, there are a lot of error codes. I want 0 to 499. Seems like a good place to start. And so while that loads, I'm just gonna say, so basically it's looking for this specific error. And if it's that error, then it breaks out of here and it writes the number of decrypted message and it returns some true or false. basically if the count was 0 or not. What's the specific message it's looking for? I'll show you one way to find it, and I can show you another here. So here's OX12, error, no more files. Perfect. So if it gets to the error that is no more files, then it's actually what it was expecting and it breaks out. Otherwise, it's going to print in the error message. This is where, let's see, I bet it works on this one. So equate, what is equate doing? Anytime you click on a constant integer value and you do set equate, it's going to give you, so in this case, OX12, all of the constants that it knows of from the Windows API that are OX12. And what I want, I know that since I'm looking for something here, all these error messages, the constant names start with error underscore. So what I can do is filter on error underscore and see that error no more files is an option. If I click OK, it actually is nice. Ghidra is nice enough to fill that in for me. For the ones that it didn't have, that I showed up here earlier, I could go there's actually a way you can come down here and add it in the data types manager. It's not. I've done it before for places. I think actually the 9th challenge this year is actually really useful to add a bunch of equates in there. But in general, most of the time I don't end up doing that, or I can just add a comment that says what it is if I want to see that. Okay, so regrouping. We have a pretty good idea how this is all working. It's passing each file name into the file names go in here, and then the names plus keys go into this one. So I'm immediately interested in this function right here. So let's rename this function decrypt file. Again, I don't totally know that, but it seems pretty clear at this point that's what's happening. Dive in and look through what it's doing here. So again, I got these create file A. Let's start with what were our parameters passed in. This one's a little interesting because I didn't do as detailed a job there. I know that the third parameter passed in is the user key. The first one is the file name, and I don't quite know what the second one is. So let's rename these here. Rename variable key. Let's see. I'll leave these. So this is the encrypted file. And then I don't know what the second one is yet. And I could go back and try to figure out what it is, or I could look in here and try to figure out what's happening. So I've got create file A. It's got a lot of stuff. So let's look it up. And what's happening here? So it's taking in the encrypted file, and then it's taking in OX 8000. And let's see, I might be able to use, it's hard to know. Again, I could try to use the equates to figure out what's going on, but I don't even know what the kind of constant I'm expecting here. So let's run through the parameters. Oops, scroll too fast. So I've got LP file name, that makes sense. The next one is DW desired access. So let's scroll down a little bit here. The request, it can be generic read, generic write, or both. So let's see what this says. We'll use our equate. We know it's generic read. Perfect, okay. And so I got another one right down here. I'm gonna do the same thing. I'm guessing this one will be generic write. All right. Ooh, Firefox crashed on me. I wonder if that was if something was wrong. That's why I was going so slow. Let's go. The next thing after that is sharing mode. And the values are file share delete, file share read. So we can see all these constants start with file share, blah, blah, blah. So let's come up here and do equate again. There's file share read. Looks good. And let's see what this one says. Was there another file share write, file share read, file share delete? Oh, it's 0, and 0 doesn't have a name. Okay, so that's why it's not showing up there. The security attributes are 0 in both cases, so I don't have to worry too much about that. That makes let's see, security attributes. If the parameter is null, there cannot be inherent. Okay, that's not too stressed about that. The next one here is this DW creation disposition. So basically it says like, what do I do if the file already exists, or that kind of stuff. So for this one, I've got a 3, which looks like open existing. We can verify that. And for the second one, I have a, did I loop? Oh no, I have a 2, which is what? Create always. And this is an example of like these, most of the time the constants from the same field will have the same name, but that's not always the case. So you can't always just start with create or blah, blah, blah. It's interesting. I was talking earlier, I've wondered about what happens if I didn't delete those files and I wanted to run it again. This creates a new file always. So even if it already, if the specified file exists and is writable, the function overwrites the file, the function succeeds, and it sets the last error code. If the function does not exist, a new one's created and the last error code set to 0. So it's going to stomp over my old files either way. All right, and then what is this 80? Let's go back here. What's the next parameter? Just going down. Flags and attributes. Anything in here I want to worry about? There's 80, file attribute normal. Okay, we can be nice and complete here and go ahead and put that in. Equate, and since it's the same, since I already used that one, it'll put it towards the top. And then the handle is okay. So it's opening up 2 files, one for reading and one for writing. So I'm gonna already say this is almost gonna certainly be the output file name. All right. And that makes sense actually. If I think back, I can jump out to my previous function. This file right here so this function 401030 takes in the file name of the current file and a buffer local 54, which is a 64 character buffer, and it's never been used before that. So it's uninitialized. So it's almost, whenever an uninitialized buffer is passed into a function, that almost certainly means that that it's going to be updated during that function. So in fact, I can rename this now, get output file name. And I can feel pretty confident about that. Again, I'm making an assumption here, but it feels pretty good. And again, if things start to not come together, I can always go back and question that. So we're back in here. We've opened up, let's rename this to enc file handle, and we'll call this out file handle. So we've got these 2 handles now. If either of them fail, it's going to call to print and exit. That's fine. Now we enter a while true for read file. So again, let's come back here and open this up and see what we got. So read file takes a handle to a file, a buffer that's used for output, so it's going to write into that buffer. It takes a number of bytes to read, and then it has an optional number of bytes read to be written. And then we're passing 0 into this LP overlap, so we're not going to worry about that. Okay, so this right here is going to be the output buffer. And so we're only reading in 8 bytes. That's why it's undefined 8. That makes sense. Okay. Rename variable buffer. Then it reads 8 bytes. This will be the number of bytes written. And again, the reason that it does that is because if it tries to read, let's say my file was 12 bytes long. It would, the first time it read file, it would read all 8. But then if it later called read file again, it's going to read 4. And then the next time it calls read file, it's going to read 0. And so, in fact, this will be, let's see, what's the return value on read file? A Boolean. If the function succeeds, if it fails. Okay, so we'll just call this success. Okay. So if success is 0, if it doesn't succeed, it prints and exits. Otherwise, what is bytes? Okay. So it's reusing this variable here. So I'm going to just change this to rename variable num bytes to make it a little bit more generic. Okay, so if the number of bytes is 0, it breaks out of this while loop. Otherwise, it's going to call this function and pass it the buffer that it read and the user key. There's no return value. And then it's going to write file to the output file. It's going to write that buffer. It's going to write the number of bytes, so how many bytes it read. This will be the number of bytes written. I think I can probably safely name this one, although it's not used ever again, so we can just ignore it. And then again, if it fails it to write, it exits. And then once it's done looping, it's going to close some handles. It's going to write some stuff, which again, I'll jump back to my Windows box real quick. That would make sense. So as it does this file, it's going to need to write this line for, for each file, it's going to write a line. And then it's going to return. So what I'm really interested in is this loop right here is reading 8 bytes at a time. It's doing something in this function, and then it's writing this same buffer. Again, I can say it must be changing this buffer in the function, because otherwise this would just be writing the exact same thing out to the file, and that clearly is not what I saw in the real world. So let's go ahead and rename this function decrypt buffer. All right, so I've got decrypt buffer. It takes a buffer and a key. We know the buffer is going to be 8 bytes or less, and we know the key is going to be 8 bytes or less. And let's go ahead and dive in there. This one, unlike the other ones, there's no API calls. It's just simple and mathy. I already forgot what the order was. Let's see. Buffer first, then key. So let's go ahead and rename buffer and key. So there's 3 simple variables here. I can center click on a variable to get it to highlight where it is. And see what we're doing here. So it's some kind of while loop here. And this is one of those things where it's probably incredibly simple. It's just making it look complicated. So this, anytime it initializes something to 0, just for simplicity, I like to name it I. It makes it more readable to me. So bvar2 equals I. So that's almost like another counter kind of thing. So we'll call it J. It's going to say while bvar2. So it's going to, so while in this while loop, it's first going to set J to I, and then if J is less than, let's make this decimal 8. While J is less than 8. So it's going to go over the whole key and buff up to the key and buffer. What's it going to do? So this right here, this is going to be a byte. Let's rename this byte, and that is going to be, so anytime you see like a buffer, which is an address to a string, to where a string starts, plus I, you can think of that as like buffer square bracket I square bracket, or close square bracket. So it's like getting the ith value of the buffer. So here it's taking the ith value of the buffer and XORing it. That's what the up caret means, by the ith value of the key. Pretty simple, and it's storing that as byte, and then it's doing some shifting stuff. And that's probably what it was talking about with the rotate right in the hint at the beginning. So this is taking the byte and shifting it up by, so J and 7 is just going to make sure that J is always between 0 and 7. Because 7 in binary is 111, so it's getting the low, and when you AND something, that's basically going to take all the bits that are on in both. So it's going to get the low 3 bytes of J, which in this case is all, J will only ever have low 3 bytes, so that's not really necessary, but it's there. So we're shifting our byte up, to the left by J times, and then we're shifting our byte to the right 8 minus J times. And then we're ORing those together with the pipe here. And then after we have all of that, we subtract J. Okay. And then we take, and then we store that as I plus into the buffer sub I. And we make sure to cast that as a byte because we only want to write 1 byte, so up to 256. And then we take J plus 1 and set it to I, and we take I and set it to J. So we increment I and we return. So here we go. Here I have right now the math of what's happening when it tries to do this function. Whenever I see something like this, before I can try to figure out how to deal with it, I always like to try to recreate it. I like to do it in Python. So I will copy, let's see, how much of this do I need? I need this while loop, really. Grab this. Let's go back to a terminal. Let's make this big. So we will do vim decrypt.py user bin env python 3. Go ahead and set paste that in. And then I'm going to Control V to do a select down a visual block, capital I to insert at the top, put in my comment, hit escape twice, and I get the comments all the way down. And let's see. So what am I going to do? I'm going to try to recreate that. So I'm going to do def decrypt. Take a buffer and a key. I'm not sure why I don't get tabbing there, but we'll deal with it. So I've got my result. I need to somewhere to store my result equals like that. And then I'm just going to do a simple loop over for I in range 8. So over my 8 bytes. We'll make it look very much like we have here, right? So we'll just say byte equals, so this is buff sub I XOR key sub I. And then let's see what the next line is. So the next line is the one that's like slightly confusing, but so we'll do, instead of setting, so I can't easily set like individual bytes in a string, but that's why I'm just going to, because I'm basically going to overwrite bytes 1 through 8, I'm just going to restore it in res. So I'll say res plus equals. And so this is byte shifted up by 7. So byte shifted up by, oh, sorry, by j, or by I in this case. Or byte shifted down by 8 minus j. I don't need this again. I don't need the and 7 because I know that j is never going to be more than 7. So it'll work out fine there. And then I need to take all of that and subtract j. That seems good. Let's actually, hold on, let's make, yeah, okay, that'll work. And then I will turn res. Well, we'll see if this works. So we were going to try decrypt buffer. Let's try a buffer. We'll pass in bytes of 8A's, and we'll pass in key of please subscribe, just like I did in the initial thing. And then we can result equals, oh, let's see, call it plain. And we will print plain. See if that works. I'm sure I made some mistakes in there, but we'll find them as we go. So, Python 3 decrypt, invalid syntax. Wonder where I'm missing something here. Oh, okay. Missing a closed parenthesis. That looks better. J is not defined. Of course, J is not defined. This is make those I's. Can't concat int 2 bytes. Okay, so we need to convert this to bytes. So let's do this. What is it saying here? It's basically saying this is when you take a byte out of a buffer in Python and XOR it, it's actually treating it as an int, and so the result is an int here in this bytes. I'm shifting around stuff, I'm doing all these math activities, but I've not actually converted it back to a byte. So to make this a little bit more readable, I do byte equals and just get over there, and now I can do res plus equals, and now I want to do byte dot 2 bytes. The size of the expected output is going to be 1, and then you next have to say whether it's big endian or little endian. With only 1 byte, it doesn't matter because there is no byte order, so I can pick either here. Let's try that, see if that works. Int too big to convert. Now you got me confused. I don't know exactly what that is. Let's see. So we'll come down here and we'll do my favorite debugging trick. Import pdb.setTrace. And what that's going to do is it's going to bring up the Python debugger right there. So let's see, what is byte? 49. Okay, does that work? What happens if I do this? That works fine. Let's continue until it fails. It's still looking okay. Oh, okay, but I happened to just guess when it failed. 799. Ah, okay. So here's the thing I didn't take into account. Cool, this makes sense. This is useful. It is making sure it's doing a lot of things really hard here to make sure that byte is only, it's writing this to it's casting this to a single byte. And so I need a way of saying only worry about the low 256, the low 8 bits. And so the easiest way I think to do that is to go ahead and just do mod 256, and that's going to just chop off anything higher. So now with this, run that again, and it prints out some bytes. And in fact, xxd test.text into head1, we can compare, and we can see that it starts with 1y, then 8e, fe, 1f, 8e, fe, 1f, 7f, 8613. So this is cool. I have now taken my I've taken the encryption or decryption that's going on in this exe, and I've recreated it in my own Python function. And that is, I mean, other than just a cool coding exercise, that means that I can now start to play with it and figure out, how do I want to attack this? So what's really useful here is I know that I've got these encrypted files. So I've got, I've got these encrypted files, and there's a couple here that I can start to guess that I might know some of what the plain text is. And if I know the plain text, and I know the encrypted text, and I know the algorithm, in this case, I can actually brute force what the key must have been. I think the reason they put Latin alphabet in here is probably to get us to try to use that as the known text. That certainly could work, although there's a trick here. It's 26 bytes long, so it's almost certainly one, each of the 26 letters. I don't know if it's uppercase or lowercase, so I could have to just solve it twice. I originally solved this, and what I will show you now is I'll use the PNG because a useful fact, so almost every file type, not something like a .text, but a PNG, a GIF, a JPEG, etc., have something called magic bytes at the top. And so if we look up file magic bytes, this will tell us like what the file headers are. I love this Wikipedia page. It's so useful for CTFs. Anytime I'm doing a CTF and I do find a file type that's not in here, I like to add it. So if we look up PNGs, we can see here that the PNG at offset 0 starts with these 8 bytes. And this is really useful because it just so happens I know I have an 8-byte key, and if I can get the key from those 8 bytes, I've got a perfectly contained full 8 bytes of encrypted text, full 8 bytes of decrypted text, plain text, and then I can get it, so I can find out what the key is. So that's the strategy I'm going to go after. We will, let's see, just to be kind of a little OCD here, we'll copy decrypt to root.py, and I'll show you what I mean here. Vim root. So we don't need this anymore. What we need is to know. So our encrypted text is equal to, let's come down here and do xxd on files, kappa PNG encrypted. We just need the first line, so we'll do a head -1, and we'll grab the first 8 bytes of this right there. And we'll put that into our Python here. We'll need to go ahead and add some /x's to make these hex things treated as bytes. That wasn't too painful. We know the plain is also going to be a similar buffer. Let's go to Wikipedia for that. Copy, paste in. Yep, and we'll again have to do the same. Get rid of spaces, add the OX. And that looks pretty good. So now I'm going to do a loop. When I first try to solve, so let's see. So I'll do a loop. I'll do for I in range 8. So I'm going to take each byte one by one. And then I'm going to do for j in range 256. And so what I'm going to do is for each byte, for each byte in the key, so 0 through 7, I'm going to try all 256 possibilities. And anytime, so when I'm in the first byte, when I try all 256, only one of those is going to take the encrypted C7 and turn it into a decrypted 8-9. And once I find that one, I know I've got the right byte for the first byte in the key. So what I can do is decrypt, result equals decrypt. And what am I going to pass in? The encrypted thing, and then the key will be key. We'll have to define that in a second, or above. And then we'll do if result sub I is equal to plain sub I, break. And what's going to happen here is, first let's set the key. So I was tempted when I first did this to say key equals, you know, something like that. Key 8 bytes. Is that actually 8? Yep. The problem is you can't change a string like that in Python. So what I actually want to do is key equals byte array. It's 8 long. So that's going to create an array of 8 bytes. And the good thing is those will be changeable. So I can come down here and say key sub I is equal to J, not checking, is equal to J. So recap them. I'm going to start with a key with an uninitialized byte array. It's probably all zeros. So key will be all zeros. But it doesn't matter because before I ever use a byte, I'm going to overwrite it. So I'm going to start with the 0th byte, and then I'm going to loop over all 256 possibilities, setting that first byte to there. Because I know that I'm actually putting this into a text console, it's almost certain that key is actually ASCII. And if this was going to take a long time, I could reduce my brute force time by, instead of doing 256, I could do like 0 to 127, or maybe even like 10 or 15 to 127, look at an ASCII table and figure it out. Or I could import the string library and use like string ASCII printable. But this is going to go so fast, I'll just do all 256. Okay, so it sets the first byte of the key to the current J, it calls the decryption, and then it checks, is the first byte correct? Let's assume 0 is not the first byte, it's going to say no, it's not going to break, it's going to loop, J is going to increment to 1, try again, 2, 3, 4, 5, until I find the right one. When I do find the right one, it's going to break, and so this J loop is going to be considered done, and it's going to then jump out, and so it's going to hit I. Okay, I increments now, so now I'm in I equals 1. What's cool is the key sub 0 is just going to be left at the correct key. And so what that means is, when I get to the end of this loop, the key will just be the key. So I can do print key, and the key is going to be a series of bytes. So I'm just going to do a .decode, try to print it out nicely. And if this works, when I run this, I should go ahead and get the key. No one trust. That seems like a pretty good key. Let's jump over to our Windows VM and give that a try. All right, so I'm back in the Windows VM. I can unlock my files. I'll put in no one trust. It says it's decrypted just like it does every time. I'll refresh over here. But now when I open up the PNG, it opens up correctly. I don't know what cicero.txt is. Maybe some lorem ipsum text, doesn't matter. Commando.vm.gif works great. And criticaldata.txt has my flag. So there's the flag. We've solved the challenge. Oh, let's check real quick. Latin alphabet.txt. It was the uppercase letters, so I would have guessed lowercase, so I would have had to do it twice, but sure. Okay, that's not that big a deal, but that could have worked too. So that's the challenge. Hopefully that was useful. Thanks for sticking with me till the end, and I'll talk to you next time.
So I'm actually back here. I realized I ended the video, but there's one part I wanted to add on to the end. I managed to do this entire problem here statically using Ghidra and then, writing my own script. But especially if you're just beginning and some of that stuff that I looked at statically might not jump out to you as obvious, another really useful tool to have is to be able to debug. And so I thought I would just show that as an example here. I'm gonna jump back over to my Linux VM. In my decrypt with key function here, I kind of skipped over the get output file name function. And I was, when I was doing the static analysis, I was able to sort of say, look, this function takes in a buffer that is not used before. And then it also takes in the metadata of the file name about the file, and it returns, and then that buffer that had not been initialized is then passed later into decrypt file. And I figured out that was going to be the output file name. It's a little bit weird because Ghidra doesn't do a great job with this function. If I look at it, if I dive in, I have clearly some kind of, it's a for loop. It's a very short for loop. If I, clearly this looks like an I. So it's starting from I equals 0, and it's going until, so a for loop is going to have 3 parts. It's got the initialization, it's got the check that happens every time, and, it even allows for this, setting of variables within the check step, and then after the second semicolon, there's the increment. So it initializes, it then checks to make sure it's allowed to keep going. It does whatever's in the loop, which in this case is nothing, it's empty. And then it increments I and does the check again. So the check here is actually setting param1. and rename this to input. So it's setting param 1 sub I equal to param 2 sub I. Oh, that's annoying. Okay, so it is going to initialize I to 0, and then it's going to loop over i's over the input one until it reaches a null, setting the output, the equivalent output to the same. So by that logic, it really should just copy the entire file name. And then, so that's fine. But then it does this weird like file data, C alternate file, a different part of the file metadata, and it adds 6 to that, and then sets that to 0. And this doesn't make a ton of sense to me. Like if it was encrypted ENCRYPTE, it's way more than 6 bytes. So it's not clear to me what's happening there. And somehow I have this output file name. So I'm guessing the Ghidra decompilation is probably not that great, or maybe I'm just missing something obvious, but let's say this is really hard to understand. This is a great case to debug. So we'll jump over to the Windows VM, and there's, one thing I want to always do when I'm debugging Windows EXEs is turn off ASLR, because without, in fact, I'll show you first. If I run X32 debug is my debugger of choice. If I go ahead and run UnlockYourFiles.exe and I run to the main, my entry point here is D91460. If I jump back to Ghidra and look at the entry point, you'll see it's 401460. And so the last 3 are always going to match, but then after that it might not. And what's even more annoying, if I rerun it here, if I stop this and reopen it, oh, it didn't change there. Okay. To be honest with you, Windows ASLR can be kind of confusing. So regardless, I want to go ahead and turn it off. And so what I'm going to do is close this entirely because I can't have it in use. And then I'm going to use this tool that I downloaded from the DDA Stevens suite. DDA makes awesome tools. Oops, let's see. I believe I have it in here. Yep, and you can just get this off GitHub. Set DLL characteristics.exe. And then all you're going to need to do is give it the -d flag, and then give it your executable. And so now, when I open this up in X32 debug, and I run to it, now it's going to, ASLR will be off, and so you can see 401.14.16. It matches what I saw in Ghidra. So that's just a useful tip. Okay, so back to what we were going to look at. What I like to do is work out of Ghidra and say, okay, where am I trying to get? So I remember I was looking for get output file here. So that was in decrypt with key, maybe? No, decrypt file. Yeah, okay. So no, it must have been in, where was I? Decrypt with key. Here we go, get output file name. So that call is made at 4013 C9. If I come back here and I find 4013 right here, C9, I already put this in place. And I can now run to that point. Okay, so now in the, it's opened up another window and it's actually asking me for a password. So I will just say not and I get to this breakpoint. And let's go ahead and make this big. I'm guessing this text is too small. So I don't remember exactly how to set this. Oops, I bet it's in options, appearance, font. Yeah, everything is an 8. Let's make everything an 18. It's going to make it giant. That's better. Okay, there we go. Hopefully you can see it now. And so we have the call to unlock your files here. We can see that the first buffer, if we right click here and follow in dump, we can see it's kind of just an empty buffer. And then the second thing being passed in is kappa.png.encrypted. And if we just use step over to run that function and come back, we can see that somehow the first, we can still go, we're still on the sizing like this all off. You know, when we look at this 19FD-F0, 19FD, let's view that in the dump again, make sure we're there. It somehow returned kappa.png ed, which is not what I, oh, it returned the whole thing, kappa.png.encrypted. So the function actually did exactly what we thought it did. It does a full copy of the whatever, you know, string 1 into string 2, or output into input into output. And so let's see, where was that? What's probably interesting then is it's probably this line that's not actually looking quite right, because then we have the call to decrypt file, 13EB. So let's come back here, move this, make this 13EB. So right here is our other call. So somehow in here something is happening. So we can sort of step through this and look. It's gonna make some space on the stack. It's going to move EAX into EBT10. EAX is 12, the length of, so 12, hex 12 here is the return value from this function, which remember is the length. So, and that is, you can see it's 1 row and then, you know, and then 2 onto the next row, so 12. Okay, this is starting to even make a little bit, I'm guessing I'm coming into clear picture now. It's moving that onto the stack, and then it moves it back to EAX. Effectively does nothing interesting. Now we get EBP plus EAX minus 5A, and we're going to put 0 there. And so we could do the math, but we could also just step over and look and see what did that do. So let's see. We should probably look at that address. When we right click here, follow and dump that, it's now a null. So you can see now, here's capa.png, and then there's a null. So what that did basically was it went on the stack, and then it pushed onto the stack the string, and then it went, I don't know where the 6 came from, but it went plus EAX minus 5A. That must be, you know, adjusting a little bit to figure out where on the stack the dot encrypted starts, and just replacing it with a null so that we get the null. It's not entirely clear how that's happening, but again, at this point I don't really care, because what I've seen is, okay, yeah, I have verified this is getting, you know, now I have, let's run to that breakpoint, now I am passing in kappa.png.encrypted and kappa.png and the password. So that is behaving just like I expected, and so now I can jump back here, and if I hadn't figured it out with confidence, I can say, you know, this is the output file name. This is actually not get output file name. Let's go ahead and rename it. It's just like, basically it's a string copy. And then this will be len string, and this is just wrong. And so we would, you know, I can come here and make a comment that, that pre-comment, this isn't good, this assembly, it's removing the, not having misspelling errors, removing the dot encrypted from the new string. And now if I ever come back, you know, in some world of coming back to this, I know what was going on here. So anyway, that was all I wanted to show, and thanks again for sticking around to the end, and I'll talk to you next time.